Okay, hello everybody. We are beginning our final test chapter on current and circuits. And so if you want to follow along with the PDF that I have posted, you can go through slide by slide with me as I make some modifications and explanations here. I don't have a ton on Edmodo in terms of practice problems. There's a few things if you go to the folders. What I'll try to do over the course of the week is find some more examples and worksheets and things that we can use as tools. But obviously, looking at slide number 1, you have um, you have you have PQ number 17 in the first two lines going along with the first portion of this chapter, and then you have PQ 18 and on line number 22, which goes along with the second portion. We'll get into RC circuits. So today what I'm going to do is go through everything up until RC circuits, and then we can dig into that in the future. So moving forward to slide number 2. Slide number 2 gives a definition of current. Current is abbreviated with the capital letter I. And obviously, as we go through our slides here, at any point, if you need to hit pause and kind of go through your PDF and kind of relive any of this stuff, obviously that's the benefit of having this on video. So hit pause as often as you need. But current is the flow rate, and it's not the speed. It's not how fast individual charges are going, but rather how many charges go by in a given second. And there's going to be drastic differences between those two things. If you think about a really wide but slow-moving river, like maybe like a Mississippi River, or if you've been down to the Detroit River, you got a massive body of water flowing, and it's not the fastest river. I mean, you watch rapids and kayakers and things like that, how fast that water's moving, but just at the sheer size of how wide that river is, there's a ton of water going by any given moment. So keeping in mind that it's the flow rate and not the speed. And your flow is going to depend on the first bullet point there. It's going to depend on how hard you push, essentially. So what is the energy that you are giving to each charge? That's the definition of potential, which is, joules per coulomb. So how much energy is each charge going to receive? And the other thing is going to affect your flow rate is going to be how much resistance the charges are encountering. So if it's really easy for them to move and flow, you're going to have a high rate. And if for some reason it's difficult for them to move, it's going to be a low flow rate. And if I put all those together, I get Ohm's law, V equals I times R. For all you Spanish speakers out there, I always think of IR as ir, the verb to go, and all the times you use it, it starts with a V, whether it's vengo or whatever. So, but anyways, V equals I times R is Ohm's law. And any device that follows Ohm's law is referred to as an ohmic device. And an ohmic device simply follows Ohm's law. So it's this nonstop cycle of what it means to have Ohm's law and be an ohmic device. But it's a nice, simple, direct relationship. So as we scroll down the page here, so our current can be determined by the amount of charge going by in a given amount of time. And with our advanced knowledge of math, we know that delta Q over delta T is technically an average. Make it a small enough time, and we get an instantaneous current. So we will at times, pardon me, we will at times come across examples where we have charge that a current that is changing. So the unit over here, the unit's going to be a coulomb per second, which is a unit that makes perfect sense, but we do have an abbreviation for that. It's called it's not an ampere, it's called an ampere because it is a French name that we are using. So say it out loud, ampere, ampere. So one of the 2 or 3 French words that I can say correctly, since it's a physics word. But we abbreviate it with a capital A. We will oftentimes refer to them as amps, but that is our unit. So if we continue moving on down, so if we take our equation, if we take our derivative up here, and we just rearrange it, what we end up with is the amount of charge that flows by in a given amount of time is going to be the integration of the flow rate multiplied by the time interval. And a few points of note, a few definitions, if you will. Conventional current is considered positive charge flow. We've already talked about that, positive charge flow. We've talked about that previously, and we know that it's not correct. We know that technically we have a negative that's actually doing the moving, but a negative moving left and a positive moving to the right would be caused by the same type of voltage, and it produces the same end result. So we will consider literally positives moving. So these positives are going to, the phrase we like to use is pinball. They're going to pinball their way through the wire, which means they're just kind of bouncing off things, rattling through, working through. And you know, it's really not entirely unlike going through a crowded hallway. You're walking through a crowded hallway, whether it's at school, whether it's at a sporting event or whatever else, and you're kind of just bouncing off the people around, slowly shifting your way forward. And everybody moves all at the same time. So my example here, and if you were in my class last year for physics, we did this, was a Cedar Point line where everyone's standing, the front of the line starts to move, and then eventually the middle starts to move, and then eventually the end starts to move, and the front of the line stops, but the back keeps on going because there's room. That is not how charges work. If that's how it works, you'd flip the switch to your lights, and you'd have to wait for the charges in the lights to finally start moving. That's not how it works. Instead, it works like a marching band. Everybody steps forward at the exact same time, knowing that they're not going to step on the person in front of them because they know that person is stepping out of the way. That's how the charges work. So as soon as you flip the switch, every single charge in the system starts pinballing its way forward. We call this the drift speed or the drift velocity. And it might be surprising to know that the drift speed is actually rather slow, so 10 to the negative fourth meters per second. So going back to flow rate, imagine if I'm standing outside my classroom doorway and it's a busy day and all these kids are pinballing their way through. If I'm looking across the hall, how many kids go past my door in a given second? Well, I might have 6 or 7 kids all walking next to each other, and so in 1 second, 6 students went through. Doesn't mean they're moving fast. It just means that that's how many had gone through, as opposed to having someone running through with a speed or something like that. So another way to kind of relate that. So continuing on, I think we're on to page number 3 now. So looking at drift speed is it can be calculated very simply by simply doing distance over time. So we rearrange that over here to figure out length equals speed times our time. And now what we're going to do is we're going to begin using some different definitions just to kind of look at our information different ways. So number 1, what we're going to do is look at this particle. Hey, I'm not sure what just happened there. I apologize. It just jumped on me. Okay. Particle concentration. Particle concentration is kind of what it sounds like, the concentration of the charged particles. And so our definition right here is capital N. We're going to have lowercase n later on. Capital N is the number of particles per volume. And so if I look at my drawing over here, I've got a cross-sectional area A right there. That's the thickness of the wire. I got the length of the wire. So if I multiply those together, that's going to give me my volume. So if I want to know how much charge I have, Q right here, if I'm trying to find the amount of charge, simple. How many particles do I have? What's the charge of one of those? Elementary charge, E, we know that one. So N times volume times E gives us the amount of charge going that we have in one particular segment. We're going to look at it moving in a second, but right now all I care about is literally how many charges are in that wire. I know that if this positive charge right here flows off the wire, I'm going to get another positive down here flowing onto the wire. So this amount of charge should remain pretty consistent. So if I scroll down, what I have here is the amount of charge that we have is going to be equal to how many, what my particle density is multiplied by that volume. That's going to be how many particles I have. The charge of one individual particle is right there. And the whole reason we did this is because we're trying to get back to current, to flow rate. So all I have to do is say, all right, now that I have Q, divide it by time. And obviously I see over here my time's going to cancel out. And I end up with a way to calculate our current. We take the particle density, we take the elementary charge, the drift speed that we have, and A, which is going to be the cross-sectional area of your wire. So in looking up here, we have length turning into speed times time right here. Length equals speed times time. I always call this the Nevada equation because when I see it, I see the word Nevada in there. So that is a given for us. Okay, so now we're going to move on to I think we're on number 4 now. Current density. Current density is capital J. So we have impulse, which is capital J vector, and now we have current density, which is just capital J. I've never seen current density and impulse used in the same question, so there should be no issues with them showing up in the same grouping of equations. Current density is going to be the amount of current going through a particular area. This is the cross-sectional area. Cross-sectional area is basically the thickness. So if you were to take a wire, cut it, and look at it from the end, that's how thick your wire is. That's what the cross-sectional area is. So we have I divided by A right here. The unit is going to be the amp per meter squared. There is no abbreviation for that. So we take our Nevada equation and we divide out our cross-sectional area, and we end up with the equation to find current density. So N times our elementary charge times our drift speed. Scrolling on down here, if we were to put these into an equation, and this equation, or I'm sorry, into a graph, and we wanted to graph the electric field versus our current density, we're going to get a nice straight line. And what I notice is if this line, let's see if I can grab this line here, if this line starts to get low, I end up with a very, very big current density. Current density J. Sometimes I say charge density mistakenly, and you guys aren't here to correct me, so I got to catch myself. So if I have a very, very large current density, but require only a small amount of electric field, that means the charges flow through rather easily. If I have a line that's much, much steeper, to get the same amount of current density, I'm going to need a huge amount of electric field, a huge amount of push. And therefore, it means that whatever wire I'm going through must be really challenging to go through. And so what we find is that our slope represents a physics characteristic known as resistivity, Greek letter rho. This resistivity is it's a unique value to each individual material, and it's basically how easy is it, or how hard is it, I should say, to go through a material. So resistivity, the bigger the number, the harder it is to go through. So if we come down here, an insulator is going to have a very high resistivity because the charges can't flow through it very easily. A conductor is going to have a very low resistivity. There is also a concept that we don't use as much in terms of our equations called conductivity, which is kind of the opposite of resistivity. So a perfect conductor is going to have zero resistivity or low values, and a perfect insulator is going to have very, very high amounts of resistivity. So the bigger the number, the harder it is to flow through. So if we look through here, we end up with, and it looks like I've kind of jumped ahead and have skipped something in my notes here, but if I look at the unit, so a volt per meter, that is our electric field, an amp per meter square, that is our current density, and so if we go through, we get a voltmeter per amp. A volt per amp. If we go back to, forgive me, if we go back a couple slides to Ohm's law right here, one thing that I don't have listed on here is the unit for resistance. This right here, resistance and resistivity, they are different. They are related, but they are different. The resistance is measured in ohms, which is the letter looks like that upside down horseshoe, or whatever you want to call it. That's the capital letter omega. So that right there is called an ohm, O-H-M, obviously named right there, going along with Ohm's law. So that is the unit for resistance. So going back forward to where we had our current density, scrolling back down, so we have an ohm meter. So ohm meter doesn't really have a lot of meaning to us when you say it out loud, but that is the unit of resistivity. So we come over here, and first we end up with an equation right here, and that equation is basically the equation of our graph up here, which is the electric field is going to be equal to the resistivity times our current density. If I come down here, I know that a field is the potential divided by the distance between our two locations. So in this case, it's the length of our wire. I have my current times my divided by my area for my current density. And so if I come down a little bit more here, I have I and L switching places by just doing some algebra. And when I have V divided by I, Ohm's law says that is our resistance. And so here is another equation that's given to us. We always call this the player equation because it kind of looks like it spells out the word player. So what does this mean? It means that our resistance for a given wire or a given conductor is going to depend on the actual resistivity of the material itself, how long is your wire, and how wide is your wire. The wider the wire is, bigger A, lower resistance. Think about this in terms of a soda straw. The wider the straw, the easier it is to suck soda through. Really, really teeny, skinny straws like the coffee stirring straws that you've used from time to time, real difficult to draw fluid through there because of the area. Very similar in terms of an analogy. Length, same thing for length. The longer it is, the more pinballing is going to happen, the more collisions your charges are going to have, and so for that reason, the longer it is, pardon me, the more resistance you're going to have. If you ever had one of those crazy bendy straws, not just a bendy straw at the top, but one that has like all the loops and twists and curls and everything else, next time you have one of those, take a mental note of how hard it is to draw fluid through that, because if you were to take that straw and like open it all the way up, you might have a straw that's, probably not quite a meter, but maybe a half meter long, super long straw. That's why it's so hard to draw fluid through there than if you were to compare it to a normal McDonald's type straw. Over here on the right hand side at the end, this right here, just concepts to know, nothing that's going to be on the test. That's not an equation, but resistance is going to be proportional to our temperature. The hotter something gets, the more resistance it offers if it's a non-ohmic device, which is why your light bulbs, if you were to graph your potential versus your current, as the current gets higher and higher, your potential goes up, and you get this curve, a non-linear, non-ohmic device. So if you're cramming for the test, everything else, I'm going to suggest this one right here in the box. Not really high priority. I have not seen anything involving this, and if there is something that involves this, they're going to give you the equation. But basically what you have here is just a shifting of what your resistance is as it gets hotter and hotter and hotter. And this is also something that is unique to each individual material. Okay, so I think we're on slide number 5 now. We are on slide number 5, moving at a snail's pace here. Slide number 5. So this new term, electromotive force. The electromotive force, called the EMF, it has this script, capital E right here. That's how we show it. This is the actual cause of charge flow. This is what we've been using all along, but we haven't called it the EMF yet. It's not actually a force, it's an energy ratio. How much energy do we give each particle? So we recognize that as a voltage. So we've been calling it voltage all along, which is fine. But technically, the actual push is coming from the electromotive force. And so basically what we've done is up until right now, we've looked at a battery as just a pump. We said, okay, this battery just does pushing. That's all that matters. It's like a little device. You put it in there, and it just pushes those charges. Well, in all actuality, the battery itself has some inner demons, so to speak. It has some inner resistance. So this is the positive end up top, and this is the negative end down below. Inside our battery, we're going to have this red electric field, which is the exact direction we don't want our charges to move. So what is it that allows our charges to A, not move with the red arrow, and B, actually move the air quotes wrong way so that it continues to pile up positives on the top? And the answer is you've got this non-electrostatic force. This is the force that is responsible for pushing our charges to a higher potential. It's pushing them uphill, so to speak. Things shouldn't go uphill. Well, you must have some other force. You're going to get this non-electrostatic force from the chemicals inside your battery. So The chemicals push charge the wrong way up to the high point. Now, there is, over on the right-hand side here, there is internal resistance. There is resistance inside the battery. As your positives literally travel, watch the arrow, from the negative side to the positive side, there is going to be resistance. That resistance is referred to as internal resistance, and it's going to be lowercase r, measured in ohms just like any other resistance. So what we're going to find is that inside your battery, you have this electromotive force, E, giving us our voltage, but we're also losing some voltage because of this internal current. Until today, we only cared about the end result. All we cared about was the output. How we got that output didn't matter to us. Well, what was happening is inside you got something doing the work, pushing the charge where you want it to go, but there's also some resistance that it has to encounter. When you have no current, you have no resistance. V equals I times R. If there is no I, there is no V that is lost right here. There is no V that is lost. So, scrolling down a smidge, right here, this is our battery. A to B, there's our battery. If you don't have it connected to anything, your voltage and your EMF are the same. I don't know about you, but I've had a voltmeter and I've tried to test out batteries to see if they're alive or dead or if they're useful or not. Well, here's the problem. When you test it out, there's no current going through the battery. Even dead batteries, unless it's like completely dead, even dead batteries are going to give you a good voltage reading. As soon as your current is not zero anymore, now we have going from A to B, I've got this right here, my EMF, giving me some energy, so to speak. It's a ratio, but we're going to call it energy. And we got this right here, this current and this internal resistance, taking energy away. So if I get 12 volts put in, but I'm losing 2 volts to my internal resistance, I'm going to have a battery that's only giving me 10 volts. And like I said, until right now, all we cared about was what was the potential given to us by the ends of that battery. So this internal resistance increases with use and age. That's why batteries die. Batteries that are really, really old will slowly die. Batteries that are used a lot will die quicker. Usually temperature can speed that up, so if you keep your batteries cold, they actually last longer. It doesn't make sense when you're talking about your phone battery because it's cold outside and your phone seems to die quickly. It's a different kind of scenario there, but if you were to take your alkaline batteries, your D cells, your energizers, your Duracells, and you throw them in the fridge when you're not using them, they will actually maintain their life a little bit longer. So in moving down here, just another way here of explaining everything. So the voltage of the battery itself that we are getting is what's left after we lose some. Now we have this term over here called the short circuit. Short circuit is basically where you have a circuit that offers up very little to no resistance. So usually it means that your device that you're trying to use, your light bulb or whatever it is, somewhere wires got switched around and it's basically not being used. The current's able to bypass that light. Current's always going to take the easiest route, so if there's a route that goes around the device that's going to use up that charge, then it's going to go that way. So what happens with the short circuit is you have very low resistance, which means your current, V equals I times R, your current goes really, really high. And when it goes really, really high, right here, this internal resistance will take away a lot of your energy, basically all of your energy, because I is going to reach a very, very large value. It's going to reach a value that's high enough where I times R on the right is going to equal the EMF on the left. And what happens? Your battery shorts out and can't push any more charge. And hopefully you have a circuit breaker or something there so that it doesn't melt up your battery. So here would be a graph of what it looks like. So when you have an open circuit, all of your potential, your EMF is going to be there. And when you short it out, you're going to have no voltage coming out of the battery because it's all being used up internally with that high current. So to end this slide here, for a charge Q to complete the path, so think about it, one charge is going to go all the way around at some point. It's going to start somewhere. It's going to connect to a battery. It's going to start marching. It's going to start moving. And it's going to eventually make it all the way around. So that means wherever it is at the beginning, it's going to be the same spot at the end. which means that it's going to use up energy as it goes through the circuit, but it's got to gain energy somewhere. So this thing that's going to give us our energy is going to be the battery, this EMF. It's pushing our things the wrong way. So if you guys remember the toy that Dylan bought me, the little penguin toy, penguins slide on down because gravity pulls them. They're not going to go to the top without some help. And so what's the help? The battery lifting the penguins by using the little ladder system that it has. Okay, so moving forward here. So this is basically just another slide doing the same thing. So this whole file you're looking at is last year's. So I don't have the ability to make good files with my little laptop here in terms of my handwriting. So this is last year's file. So this looks like just a consolidation of everything, whether it's an open circuit, short circuit, how to figure out what you get from the battery. So moving forward on to slide number 7. So slide number 7 is a continuation of our electromotive force here. So your sources, there's a lot of different sources here that you can have, and what does it do? Basically, it's taking one kind of energy and turning it into electric energy, which can we then transfer to the charges. So battery, it's chemical energy. A generator is going to be some kind of mechanical energy, which can be, basically something moving. And we'll eventually talk about magnets and currents and all that, but basically you take a magnet, you take wires, you move them past each other. So if you can get them moving past each other, and usually we find the most efficient, effective way is with circular motion, get something rotating so that the magnet comes close and far away and close and far away, or the wire gets closer, farther, closer, farther. Basically, if you can make something spin. So how do you do that? A wind generator, a turbine through a dam, or you heat something up, or you heat water up using some method, and you use that heated steam to turn a turbine, which is why you can use coal to boil the water, you can use oil burning to boil the water, you can use a nuclear reaction to boil the water. So all of your more standard power plants are going to use some kind of method to boil water. So technically the coal has chemical energy, the oil has chemical energy, the particles you're using in a nuclear power plant have nuclear energy, and then you're going to convert that into mechanical energy by spinning things, and that turns into electric energy. You can use solar energy, thermal energy, etc. So some symbols there. So wires, capacitors, resistors, little zigzaggy. Our EMF is going to be the same picture we've had for a battery. It's going to be pretty common for us to have an EMF and an internal resistance kind of put together. And we sometimes put a little dotted line around, like I just did previous slide right here. Nope, 2 previous slides ago. The little dotted line here. So that kind of represents the housing of the battery. And then there's a resistance inside. So it's common to see that. So don't be surprised if you see something like that. We're going to talk about voltmeters and ammeters. This is a meter to measure voltage and a meter to measure the current. We don't call it a current meter, we call it an ammeter. So slide number 8. As we always end up doing with power, we're going to give it just a few seconds of our time and pretty much never use it again. That's not fair though, because we actually do use power a little bit more often when it comes to electricity and light bulbs and things like that. So we defined it previously as work divided by time. We know that could also be energy right here divided by time. So we're going to be looking at the energy output. So if I go through and I look at energy being charge times our voltage, and now we have Q divided by T giving us our current. So basically right here, this is our power equation. Power we'll use, we know it's measured in watts. We can do some substitution between the two equations here to get some of these. But we come down here, these are the equations given to us on our sheet. Power is going to be useful, which are talking about the brightness of a light bulb. Power is measured in watts. Watts is how bright your bulb is going to be, how much energy is being expended every second. So that's why we do use power a little bit more often than we do in our mechanics section. So it's, I believe we're on slide 9. I can't believe I can't remember from slide to slide. Slide number 9. All right, Kirchhoff's laws. We talked about these last year, and I don't remember if I used the phrase Kirchhoff or not. But basically, the things we've talked about in the past were the loop rule and the junction rule. Loop rule says all energy is consumed by the circuit. So basically that means that as a charge goes through, it can't just go halfway. It's going to go all the way through, and every single bit of energy is going to be used up. So if you have a 12-volt battery, going from one end of the circuit to the other is going to use up all 12. Nothing is saved. That loop rule also says that I do have to ration my voltage so that every single part of the loop gets a little bit of voltage to make the charges move. Wires are easy to go through. They're going to get a teeny tiny, almost unmeasurable amount of voltage. And then things like light bulbs and other things are going to use much greater amounts of the voltage. You add up all those voltage usages, and it's going to be equal to the total voltage of the battery, or at least the output of the battery. So if I have a battery giving me 12 volts, I might use up 4 volts for one device, I might use up 7 volts for the other device, and I might use up 1 volt for all the wires combined together. Add them all up, and I had 12 and I used 12. The junction rule makes perfect sense, at least to me. I think when you think about it, all the current coming in has to equal all the current going out. And this is when we start seeing splits in the wire. So if I have a wire carrying 2 amps and it splits into 2 wires, those 2 wires together have to have 2 amps. Depending on how the wires are designed, maybe it's a 1 and a 1, maybe it's a 1.5 and a 0.5 for the other. But basically this comes down to right here, conservation, which is to me why it seems to make perfect sense. It's simple conservation. We have these little positive charges moving through, and you can't have them just all of a sudden disappear out of your system, out of your circuit. They got to be around. So when I come down here, these are some of my little diagrams here that are designed to try and help us figure out what this means. Loop rule says that we are going to go through and we are going to have the same amount of potential used up for any, why does it jump like that? Frustrating. Any and all loops. So if I have a parallel system or multiple branches, every branch has to use up the same amount of voltage. So if I come down here, this is a side view of water flowing down. Maybe it is a water park and it's a water slide. Maybe it's a river I'm looking at. There's lots of different ways for you as the water slider or the kayaker or the canoer or the boater. There's a lot of different ways to go from the high point down to the low point. You can have a red, constant, non-stop slope. You can have a really steep slope here in blue where it levels off. You can have something that's kind of wobbling like the black. That's the loop rule. You have to use up all of it. Think about if you were on this water slide. You're going to walk up through the ladder. There's your EMF. And then you're going to use it as you go down the slide. And once you start up there, once you start up the stairs, get to the top, when you start coming down, you can't choose to stop right here. You go all the way down to the bottom. It's a complete closed circuit, a closed loop. And again, we had those little penguins kind of marching up and then going down. And unless I turn off the actual power, the penguin can't only go halfway up or halfway down. It's got to do the whole thing. Now, if you look at this in terms of water, this is exactly how a lock system works. So this, if I take away some of this yellow so it's not so distracting, if I take a look at, let's say, the blue. Let's say the blue is Niagara Falls. This is obviously a boat can't go up Niagara Falls. This right here, way too steep for a boat. So what do? You have a lock system. Lock system is over here in green. This right here is how a lock system works. So your boats that can't go up a waterfall, they get lifted up with a lock mechanism, and then they motor forward. They get to another lock system, and they motor forward, and they keep on doing this stair step. If it's a small little stint of rapids, like in Sault Ste. Marie, you have one single lock, the Sault locks. It lifts a boat, I can't remember, 20, 30 feet. It's not a huge amount, but it lifts up your boat. If you've never been to the Sault locks, it's, you can see, you can walk right up and watch the boats go up and down and see how fast it is and how simple it is. And they don't use any pumps. It's just all using gravity, which is like a little scientific cheat, which is awesome. But or you get something like the Welland Canal, which is how you get around the Niagara Falls, and you got this right here. You've got lock after lock after lock after lock after lock. And you got lock number 1, lock number 2, and I don't go to the Welland Canal nearly as often as I go to the Sioux Locks, and so I can't recall exactly how many locks there are, but you've got like the Lock 7 Motel, which is a little motel right next to lock number 7, and you're right in a little downtown area, and there's a big freighter going through getting lifted up. So anyway, that's an example to try to help understand the loop rule. If I continue on down, this right here is an aerial view of a river. It's not the greatest looking picture of a river, so I've got, get these little lines out of the way here. We're going to use these lines in a second, but let's get them out of the way. So basically, you've got the water flowing through here. This right here is my river. I can't really color code it. This is an island. So some kind of a weird shaped island. I can go route A or route B around the island. The junction rule says that I'm going to have the same flow rate in and out of any location. If I look at one single location right here, this first dotted line, the current coming in right here and the current coming out right here have to be the same. And there's one single route, so that's kind of a Captain Obvious kind of a, yeah, obviously there's one single river, so when it comes in it goes out, yeah, you got to have the same. Where the junction rule comes in is when you start to put this line right here. This line is my detector. How many gallons of water goes by every second across the entire river? Well, I have a value right there. I'm going to have a value over here, and every single one of these lines should all be the same. What happens though when the water splits and goes around our island? Well, I'm going to have some flow rate, some gallons per second. So instead of coulombs per second, it's gallons per second. Instead of the amount of charge, it's the amount of water. So route A, I might have a particular amount of gallons per second, and route B is going to have some gallons per second. And what I'm going to figure out is if I do A plus B, that is going to represent the total flow of the river here, hold on, here, and here, and here. So the junction rule would say that my current coming in, call that current I1, is going to be equal to IA plus IB. IA plus IB is going to be equal to the current down here as it leaves this little area of the island. So that's the way I always like to look at our current, and it's real common for us to look at it in terms of water flow, just because we have rivers and gravity, and it always kind of helps. So I believe we're on question number 10, looking at series versus parallel. So we know what series is. We know series means it has one single path, so my picture right here shows what a series would look like. I have to have the same flow rate everywhere. It's the world's easiest junction rule. It's a junction rule with no junctions. So it's the current's got to be the same everywhere. And the voltage has to be shared because of the loop rule. We mentioned if this thing gives out 12 volts, I got to use up all 12 volts. That means R1 gets some and R2 gets some, depending on how difficult it is for those resistors to, or how much they resist the current flowing through. So if we scroll down a little bit here, so what we find is similar to what we had done with the capacitors, which is why we put so much time into capacitors to make this a little bit easier, is I have my constant current. Try that again. Keeps jumping on me. So right here, I've got my constant current, kind of like in a series for capacitors, we had a constant Q. Well, now we have constant I. The voltage had to be shared amongst your capacitors. Now your voltage is shared amongst your resistors. And if we do this right here, just like we did for capacitors, and we use Ohm's law, and the current's the same everywhere, we get a way to find the overall resistance in series, sum total. Notice that's opposite of what a capacitor is, right? Capacitor, it was the parallel, that was add them all up. Or a resistor, it's in series, you add them all up. Think about it. If a charge has to go through the first resistor that has 10 ohms, and then it has to go through the next resistor, which is 5 ohms, that's 15 total ohms that it had to go through. So hopefully a sum total makes sense. The total resistance you're going to have in series is always going to be bigger than the individual resistors themselves. Looking over here, this tells us that the voltage of an individual resistor is going to be proportional to its resistance. That means more resistance, more voltage. I think about it as if I need, way up here, if I need the current to stay the same everywhere, I need to make sure that the narrowest light bulb or the most resistive location, I got to push really, really hard to make sure the charges go fast enough to keep up. That's why when you are looking at a river, the narrow spot is where you get the rapids. And the wide spot is where it's slow and gentle, because the rapids, they have to shoot that water through really fast to keep up. Otherwise, you're going to get a backup in your river. And we can't get backups when we do our charges. We don't get backups. So that was our series in looking at our parallel multiple branches. So loop rule says that I have to have the same amount of voltage used up for every loop. So every loop has to have the same amount of voltage. So looking at my diagram over here, so from here to here through R1, I have a branch of the river, so to speak, going around the island. R2 is a different route going around the island. Well, they still have to drop the same amount. So our voltage is going to be a constant. The current is going to be shared. If I have 1 amp going down branch number 1 and 2 amps going through branch number 2, I got 3 total amps flowing in this river. So it's like adding up the A and the B branch in our river analogy. And so we do the same mathematical process that we did last time and with capacitors to figure out that our parallel total, our REQ, equivalent resistance, is the sum of the reciprocals. So this tells us that your total is always going to be less than every single individual. So yes, that means you can add in a 1 million ohm resistor in parallel and it will lower the resistance total. That doesn't seem to make a lot of sense. We'll get to that in a second. Over here, our current is inversely proportional to the resistance. What does that tell us? It tells us that the object with the lowest resistance is going to be able to allow the most current to flow through with limited restriction. So basically, the wider part of the river is going to get more water than the skinnier path around the island. So that's why path A probably was carrying more water than path B. Now when it comes over here, every single time you add another resistor, mathematically speaking, it makes the total get even smaller. My analogy has always been a highway. If you've got a 4-lane highway, traffic's going to flow at a particular rate. Every time you add a 5th lane, a 6th lane, a 7th, every time you add a lane, all those cars are able to spread out and move a little bit faster. I can get cars going through at a greater rate. Even if one lane is lousy and only one car dares to go there, that did still technically lower the resistance a little bit. So if it's a lane that has a dirt road or it's potholes or there's a bunch of rusty nails or whatever else, you know there's some idiot that's going to still try and take that route. That person right there just made the whole rest of the group flow just a teeny tiny little bit easier, but still mathematically a little bit easier. So we have a list going back a slide, I have a list back a slide. There we go. So we have a list of information for series. We have a list of information for parallel, just like we do for our capacitors. Some strong similarities when it comes to V and I. If I replace I with the letter Q, a lot of similarities there. And the equivalent values, the equivalent totals, these down here are similar but opposite. Right? So continuing forward, brightness depends on which variable. So we already mentioned that earlier. It's going to depend on our power, on the watt. So we have our P equals I times V here. So current goes up, there are more charges to give off light. I always kind of go with a light bulb analogy. There's more charges to see, literally more going through. If you have a greater amount of voltage, that means each particle has a greater amount of energy. Quite frankly, what it means is they're moving faster because they got to get jammed through that wire. You got to push really hard to jam them all through there, and so you basically have faster moving particles, more energy, more light given off. So how many particles do you see? How much energy does each particle have? Those are the two things that are going to affect your brightness. So when we come down here to the bottom, kind of more of a practical thing here than a mathematical, is what happens when you start to add more and more light bulbs. Well, if you add them in series, you're going to increase your total amount of resistance. That's going to slow everything down. Not only that, your voltage, your 12 volts from the battery or whatever it might be, is now going to have to be shared. Add in a third, a fourth, a fifth light bulb, and each individual bulb gets less and less and less voltage. So your current is less because there's more resistors, your voltage is less because it has to share, and so what happens is you end up with a dimmer bulb. Everybody likes to say that old Christmas lights are in series. I have never seen Christmas lights where one goes out and they all go out. I've seen it in the movies. I've never seen it in person in real life, but I'm sure there's got to be some truth to it. You don't see anything really connected in series, ever. Not in terms of any wiring in your house. When it comes to a parallel, every time you add a new one in parallel, you actually decrease the total resistance that the battery feels, which means that it has to push out more and more and more current. Now, come down here. Total voltage for each branch stays the same. Whether it's one branch or 5 branches or 10 branches, the voltage for each branch stays the same. So each light bulb gets the same voltage, it gets the same current. There is no difference. There is going to be the same brightness. Nothing is changing there. However, your battery has to send this current right here. Your battery has to send this current to more and more branches. So just because your individual light bulb stays the same, your battery or your EMF source has to push out more and more and more because all that current that it pushes out has to be shared. So what happens is the current coming out of the battery can become very dangerous. Current is what kills. It kills humans and it kills your circuits. It's what causes all the damage. So your total can become very, very dangerous. It can cause wires to melt and malfunction. The individual bulbs are fine, but the wire that comes out of the battery sending all this total current, that becomes dangerous. So what we have is we have circuit breakers and fuses, which are the designated weak spot. It's basically the place where the failure is going to happen. And so you can wire that in intentionally so that when you know when something happens and you have too many things all used up at once, and you maybe have done this in your house, too many things being used in the bathroom, for example. You got lights and heaters and hair dryers and radios and phones being charged up and 5 different light banks and all those different things can sometimes be too much. And all of a sudden it all goes out. Oh, we used up too much, we're using too much current, and so our designated weak spot failed before some other spot failed. The designated weak spot is designed to be easily accessible, whether it's in the circuit panel in your basement or in your garage, and you can go there and fix it very easily, whether it's flicking a switch or whether it is changing a fuse. A fuse is just a thinner piece of metal. When it comes to your ammeter and your voltmeter, your ammeter is going to measure the amount of current going through something. You need to connect it in series because in series, all the currents are the same. Now, every single device you ever use for measuring anything, you don't want it to actually affect the outcome. For example, if I'm using an ammeter to measure the current, I don't want my ammeter to affect the current because then the meter isn't really doing anything. So in that case, what do I want my ammeter to have in terms of its resistance? I want it right here to be super low resistance. I want it to be so easy to go through my ammeter that it requires such a small amount of voltage that my resistor keeps getting the same voltage that it had originally. So we have a very, very low resistance for our ammeter so that it uses up a small amount of the voltage, so small that it's unnoticed. When it comes to a voltmeter, if I want to know how much voltage is dropping through a particular resistor, I need to set my voltmeter up in parallel. So there's my picture. Now, I don't want my voltmeter to siphon off any noticeable amount of current. So how do I make sure that no current goes this way, or at least a very, very small amount of trickle goes through? I make sure that the resistance is super, super high, which maybe isn't obvious when you first think about it. How could a high resistance object be invisible inside my system? The higher the resistance, the fewer charges go that way. It's like having a 10-lane superhighway and then you open up a dirt road path and one single car goes that way. All I need is that one car to go through my voltmeter to get a reading. And that one car is not going to have a big effect on what the actual traffic is doing. Weird analogy, but hopefully it works. So you actually want your voltmeter to be a super high resistance. All right, so we're approaching the end here. I know it's been a long one, but you can use this for the next couple of weeks. When it comes to solving resistor questions, you're going to notice that it looks a lot similar to a capacitor question. What was your CEQ? Well, now what is your REQ? Instead of QVC, we've got V equals I times R. We do that for the total. And then I can do that for individuals with keeping in mind that in a series, the current is the same everywhere, and in a parallel, the voltage is the same everywhere. And just like we could do energy stored in a capacitor for step 4, we can do the power expelled by each resistor. So just like before, step 1 and step 3 are the hard thinking questions. 2 and 4 is a plug and chug. So same process that we did before. You can do the family tree, same exact thing we did before, just keeping in mind the minor subtle differences between parallel and series between the two concepts. But the family tree will also work. Now, there is another type of question that you are going to see in this. This topic, and it's when you have multiple branches. Okay, it's what's parallel. Yes, it's parallel, but you're going to have like a couple different batteries maybe given to you, or you're going to have a couple different branches with a couple different resistors. And when you see a picture, I've got a picture on the next slide, you'll see the list of things to do, and I'll try and do a couple extras throughout the week to kind of add in, or we can do some together on our Zoom meeting. But basically what you're going to do is you're going to have a bunch of different branches. And you're not going to know for sure which way the current is going to go. You might have a real strong idea, but you might be surprised at being incorrect sometimes. Basically, you are going to have to guess the direction in each branch. Simple. You can't be wrong because it's a guess. So you guess on a direction. Okay, these two are going this way, that one's going this way. And then what you do is you use the junction rule. The junction rule is going to say, kind of tell you how your currents are going to relate. Now, when you get all done with everything, what we're doing is we're trying to calculate the current in each branch. If you get an answer that has negative current, it means you guessed incorrectly and your current is flowing the other direction. So it's simple. Now, step 3 is using the loop rule for every loop. Every loop means that you add them all up, you get 0. You get a gain somewhere and you get a loss somewhere else for a grand total of 0. So you do the loop rule for every possible loop. And quite frankly, what you're going to see is you're going to see 3 branches all connected, which means you're going to have 3 possible routes. And I'll show you that in just a second. So you choose your direction, clockwise versus counterclockwise. And the last thing you got to consider is how you're going to gain or lose your potential, because the loop rule deals with potential. So in looking at this right here, this is a battery. Negative is always the low end of the battery. Positive is always the high end of the battery. So if I have my current going this way, my current is going from the low point negative to the high point positive. My battery is giving me a positive voltage. If for some reason I think or I guess or I say that my current is going this way, let's call it the wrong way through a battery. It's possible. Put a big battery and a little battery, wire them up, and I can have a big battery force charge the wrong way through a small battery. If that's the case, when I'm traveling with my current, I go from a high voltage down to a lower voltage. That's going downhill. That's going to be a negative delta V. When it comes to current, think about a river and elevation. Rivers always flow from a high elevation to a low elevation. So if this is my resistor here, if my current is going this way, then when I go through my resistor, I have a drop, a loss. So if I'm going with the current, I'm going to have a drop or a negative change, which is going to be a negative I times R. If for some reason as I go through, and again, let me slide up here, okay, you're going to choose a... Why does it jump like that? I apologize. Try this again. As this right here, so you're going to go through the loop rule, you have to choose a direction. You got to go from one device to the next device, so clockwise or counterclockwise. So if I'm going through and I'm forced to go against the current, that's not a problem. I'm going uphill. I'm going from low to high. I'm gaining potential. And I think this is going to make way more sense when I go to our next slide here. Here's an example. So black is given to you. So I've got a 10-volt battery here, a 6-volt battery here. I've got 3 branches clear that I can see. I have to decide which way my current is. So I'm going to call branch 1, branch 2, branch 3. So as you can see in red, I've made a guess. I think that current I is going left. I think current 3 is going left. They loop around, come together, and I get current number 2 going to the right through the middle. Junction rule right there. Simple. Top loop. So I've got my top loop includes the 2, the 3, and the 6. So if I start at the little red dot right there, I'm going to go counterclockwise, which means I go through the battery first. From low to high means it's a positive 6. Going with the current through a resistor is a drop. It's like going through a rapid. So I go through that, so that's going to be a negative 2 times my current. This is I times R, which gives me V. I continue through. Now I'm going through the 3 in the direction of current I2, so I get negative 3 I2. So those all add up to give me 0. A nice simple equation to use. I can do the bottom loop. That's going from green here, and I'm going to go again, right, as you can see, I'm going to go clockwise this time. So I go through the 10, from low to high, positive 10. With the current means a negative and a negative. Now, there is one more loop. It's the outside loop. You say, wait a second, now you're going to go against the current. That's okay. Loop rule still applies. So I'm going to start blue. I'm going to start right down here. Here was my blue dot. That's where I'm going to start. I'm going to go clockwise. So I go from low to high through my battery. There's a positive 10. I go with current I1. So it's going to be a negative 4I1. Continue on up. The next thing I get to is this 2 right here, and I'm going against the current. I think the current's going left. Well, when I'm going through and analyzing, I'm going to the right, which means I'm going uphill, upstream. I get a positive 2 times I3. Battery, I'm going from the high side. Sorry. I'm going from the high side of the 6-volt battery to the low side. I'm going from high to low. That's a drop. That's a loss. Negative. So those are my signs. I can obviously take 10 minus 6 and give me a 4. I now have 3 loop equations and this one right here. I swear I'm going to throw this computer out the window. That right there with my junction rule. So I got 4 equations, 3 unknowns. You're going to have to use this one with all the rest. Now if you're a matrix pro, I'm not. I haven't used a matrix, I swear to God, in 20 years, mathematically speaking, and that is not an exaggeration. So I don't use matrices, I use substitution. What you have to do is take you have to take your junction rule and you have to substitute it. If you just use my 3 colored equations here, just those 3, everything's going to cancel out, you won't be able to solve. So I take this one, put it in somewhere, and then start solving that way. So this right here has an example for you. I don't need to walk you through the math. But in the end, I know as I get 3 numbers, they follow junction rule. All my answers are positive, so I guessed correctly. If one was a negative, it just means I guessed wrong, and I know the correct answer now because I only have 2 choices. If I choose one and it's wrong, then I know the other choice is right. All right, so that puts us at about an hour. I think we'll hold off on the galvanometer. A galvanometer, if you want to check it out, read up on it, is basically how we measure things like current and voltage. If I scan a couple ahead, this right here is called a multimeter. I can measure voltage on the left-hand side here. So let's see, where's my, so let's do, why can't I do this? Let's do this right here. There we go. So I got my voltage here and voltage here. There's two different types of voltage, direct and AC. I've got over here, I've got current. So I can measure different amounts of current down here or voltage. We're going to get to that. So that is the galvanometer. We never use the word galvanometer in real life. We just call it an ammeter or we call it a voltmeter. So we'll talk briefly about that next time. But I think an hour is more than enough time for us to have had conversation. So I can do some samples with you at our next Zoom meeting or whatever it is that you think you may need. But I think that gives you a good start. That's a few days worth of stuff all at once. We have spring break next week, which means there'll be nothing new. You can keep on working through your onlines and everything else. But that's where we stand. So hopefully I will see you on Monday or Wednesday, and send in your questions ahead of time, and I can answer them there on the spot, and I can also answer them on the next video if we want. So hope everyone's doing well, and I hope to see you all in the next day or so.